you do it?
I mean, I don't.
I had to read the book.
I think I did it wrong.
How'd you do it?
Same.
Well,
It seemed easy.
I found like a delta, and then I took away what was.
How you done?
So you know this, right?
Yeah,
So it'll expand 0.5 millimeters. Right?
Expand.
Right.
all that
Yeah, when it heats up, it expands. So that's all
Oh,
pre-expansion.
I didn't know that it was expanded.
Oh, that
If it
makes
heats
sense.
up, it's gonna expand.
Oh, wait.
Right.
I was using the
So
wrong
the
one.
question is, how much
Yeah,
temperature does it take for it to touch?
There was one in the book like
Let's-
that, but it was
oh.
the exact same.
No.
I guess I didn't understand that.
You can still read Joule, right?
So,
Wait, the first one? Did you get 4716?
The first one.
Did you also get a haircut?
I did. That's like, for 716, yeah, for 716 PSI on 34.
Over 30?
At 34.
Oh, yeah.
And then I got
At 30.
2882.
how
Oh,
much
wait.
do you drink, Jorge? That's the
shoot.
question.
Yeah, it was at 30.
How much I drink? I do not drink.
Water,
I drink, I drink socially.
water, not
Water, I drink
freaking,
water a lot. So
Oh, I
far,
have
oh my
question.
gosh.
so far I have drank about
I don't
over 50 ounces.
Of
Liquid.
what? Liquor?
Liquid.
Gosh, that's not good.
Oh my gosh. All right, so 0.5 millimeters, right?
Wait.
This thing is a 1 meter long, 1 meter long. It is made of what? Copper.
No, wait, yeah. What's the aluminum?
Copper.
Copper,
Right.
copper.
If you were.
And-
Say copper.
The first one was aluminum.
Temperature goes up 50 degrees C.
But where does it start at? 0?
Don't matter.
Who knows? Who cares, right? So all this information is given to you at that temperature and then it goes up 50 degrees. Right? So, and it asks about what? Stresses?
What is stress developed in the body?
Yeah, what's the stress developed in the bar? Well, there's no stress developed in the bar until it hits the wall.
Well, you see that's what knocked me off because
Well-
there's total change in length formula, and then there's a stress.
Yeah, so it's this one, right? For thermal,
Yeah.
and that's what?
Alpha.
Alpha
Alpha L.
L
parentheses.
delta T. So what you had to figure out was like, okay, how much temperature does it take for this thing to expand 5 millimeters? So you set it up 5 millimeters, 0.5 millimeters. What's alpha for copper? Somebody has it. I don't want to look it up.
16.7 times 10 to the -6.
16.7 e to the -6. Is that in the SI system?
Wait,
Okay,
It's the same as
wait.
what's the
9.3.
unit? Millimeters per millimeter per degree C?
Meter by degrees in Celsius.
Okay, meters by degrees C.
Yeah.
What, Gina?
Wait, where are we getting 60?
Metric table?
It's a metric table.
Should be the metric table, which is the next page. Coefficient for copper, I'll just double check you, 16.7 times 10 to the -6. Yeah. Our length is 1 meter. We might need to change that because we have millimeters here. Right? So I would probably put in 1,000 millimeters for our L.
Well, my dumb estimate was just.
yes.
Whoops. You had so much fun with this, darn.
I did.
I know, it's
It
good.
seems so easy and then.
Yeah, it's always something. So delta T,
Easy.
Not really.
not necessarily in engineering, it's not the thought that counts. Something, there's some effort there, that's good.
We appreciate the part there. If it doesn't count, we
Yeah.
appreciate.
I get 29.94. degrees C. So it takes 29.94 degrees C to close this gap.
And you use
1,000
the,
millimeters in a meter? Oh my God. Yeah.
and you use
I'm
this
sorry.
formula
Yeah.
because we're trying to
I
find,
don't know.
we're involving the length.
We're using this formula because we want to know how much temperature it takes to get it to the wall. Because stresses don't occur until it's restrained. So it's free to expand this 0.5. No stresses. So for the first 29.94 degrees, there are no thermal stresses. Then it hits the wall. And the temperature goes up another, what, 20 degrees, basically? Right? Goes up another 20 degrees because we're going up total of 50. So now thermal stresses is alpha E delta T. Right? And so same alpha, 16.7 e to the minus 6. E for copper out of the metric side of the world is 103 times 10 to the third megapascals. 103 e to the 3 MPa.
Is that alpha E?
Alpha E.
Okay, just, thank you.
I'd spell E, but I just spell E with E.
Then do you use the 29 temperature?
And then I haven't put the temperature in yet, but it's gonna be what? Whatever, 50 minus the 29.94.
20.
Oh.
20.06 degrees C. I ran out of room. And the thermal stresses will be in the unit of stress in the equation, which is MPa. Because everything else drops out. This drops out with this.
103 E3 MPa, yeah?
Oh my gosh.
Dude,
I'm so sorry.
Are you okay?
not.
My
Sinus
writing,
is
my
actually-
writing can be really poor at times.
Okay, I'm not mentally here. I'm yelling at dude.
Well, at least you showed up.
That's, yeah,
Step one.
that's what counts.
E.
That's what
To
counts.
the 3
Thank you,
and-
Troy.
PA. That's better though, right?
A lot.
It's a bad A, it's a bad
Wow.
A.
That looks beautiful.
20 point, we'd be here all day if I did this. Need a 4-hour class if I'm gonna write that nice. All right, what's that number?
34.51.
34.51 MPa. That's how much the thermal stresses are, right? And then what's just some property values for copper, just so we can figure out if we're even close. So the yield is 280 MPa. I know, they screwed up. You should scribble that out and put
Okay.
MPa. So that's what I did. The table has a typo. They put KSI. So
Mine
not
says
KSI.
MPA.
So some say MPA and some say KSI, but it should not say KSI because this is a metric table.
Mega.
I thought that was funny. When I was looking at it to
Yeah.
check my
I have something to say.
Crazy.
So MPA is megapascal, right?
That is correct.
Google says that 1 megapascal is 145 kilosal. Is that right?
That would be in the front of the book. So I could just look, yeah, that sounds right. Yep. So you did it all in the US and then you converted it?
Yeah.
Yeah. Don't do that. Become one with the minute.
If there are conversions, why not?
Good. Good, good. Any other questions on the homework? What other ones did you do? You did
7 and 11, or 7 and 10.
7, 8, and 10.
Yeah.
That's what you did?
Yeah.
Want to do 7? Yeah. The aluminum wire stretched between two rigid supports. Aluminium.
Did you get
Everyone knows why we use aluminum?
Yeah. 'Cause it's super good with heat. And it's
That depends
more
on the
steel.
application.
So we use copper for transmitting electricity and we use aluminum a lot. A lot of your neutrals are all aluminum. So it's really good with thermal conductivity. It's got great stretch to it. It's got
Aviation-
great electrical conductivity.
Aviation is 2024, I believe, which is 50 years age.
Yeah.
We make it so light.
All right, so this thing is stretched between two rigid supports. Tensile stress on the wire is 5,000 PSI. $68. Yeah. Yeah. What is it at 32 and 90?
I'm telling you.
So the temperature is gonna drop to 32 degrees and the temperature is gonna rise to 90 degrees. Assume the proportional limit is 35,000. The proportional limit is given to you because that's probably what the allowable is. That's the only reason. So you're just comparing to that. Okay, so this is the existing condition at 68. And it's stretched, so it's in tension. Agreed? Yeah, yeah, so it's feeling this tensile stress. So when it cools down, what's that trying to do to the aluminum? Shrink it. So it's trying to get smaller. These walls again are pulling. So when it gets colder, it's additive. You have the 5,000 stretch, and then it gets colder. Whatever that cold thermal stress is, gets added to the 5,000.
So it should be greater than hot.
Yeah, so then when we do the hot one, what's it trying to do when it heats up?
Expand.
Expand, so it's gonna relieve the 5,000 PSI. Yeah, so you just have to figure out what that stress is. So stress, thermal, let's do the 32-degree change. It's gonna be alpha, what's E for aluminum?
13.1 times 10 to the 6.
13.1. E to the 6, that much,
-6.
that's out of the, huh?
-6.
Oh, -6, of course. That is inches per inch per degree Fahrenheit.
So we did the exercise backwards. This is 7, right?
Huh?
This is 7.
Oh, that's alpha. Yeah, we're turning them backwards, that's correct.
Okay. I was like, wait, what are we doing?
So this is E,
No, that's alpha.
alpha, okay. So the equation is what?
Alpha E.
Delta T.
Yeah.
What are you guys doing? What's up? You on drugs?
I don't know,
Kevin.
I just
Kevin.
spaced it out, I didn't.
Taking pills? Did you miss that conversation?
No, I was here.
Oh, okay.
Then we started talking about.
What's E for aluminum?
10 million PSI.
10 million PSI. 10
K is.
E to the 6,
thank
not
you.
if we, yeah, not if we do this, right?
Can we just keep it?
Wait, no,
That's
no, no.
10 million.
Wait, we want it in PSI, right?
Yeah, so I'm gonna
Otherwise,
write,
we're gonna have to translate it out.
I'm writing the units out. Whatever unit you put in here is the unit you're gonna get out of the equation, because everything else is gonna drop.
For,
Right.
okay, for E.
Yeah.
Or L.
Well, that's the other equation.
Oh, right.
All right, so then what's our delta T?
36.
The difference between 32 and 68. Yeah? So you can see the units go away. That was already gone. And we're left with this PSI. What do we get?
4716
Okay, sorry,
PSI.
PSI.
you said 4 points.
4.716.
4716 PSI, 4.716 KSI, whatever, right? But since this is in PSI, so when that temperature drops to this, we will add the 5,000 to it. And we'll get 9,716 PSI, tensile stress. Okay, so when it cools down, it actually is pulling on it harder.
Wait,
Wait, what?
quick question.
Yeah.
5,000 PSI at 68 degrees Fahrenheit, and it's getting colder.
Yep.
So shouldn't that take less PSI to stretch it?
It's already pulled.
Yeah.
To get 5,000. Now it wants to shrink.
Oh, so it takes more force to pull. it.
Yeah, so then it takes more force. It's just
It's a lot more
adding to
stress.
that stress, yeah.
Okay, that makes.
So when we heat it up, it does the opposite. The 5,000 was the pre-tension. Now we're gonna heat it up and it's like, oh, you know, it gets softer and softer. It wants to expand, it relieves that stress.
If the, what's it called, the thermal conductivity for the 90 degrees, would it be negative? So when we add the 5,000, it'd become a smaller tension?
Yeah, the whole negative, positive for stress is kind of weird. You have to figure out like, oh, are these additive stresses? Or are these competing stresses where one won't relieve the other? So you just kind of have to figure it out. All right, so we're gonna go alpha 13.1 e to the -6. Gonna go E 10 e to the 6. And now we have a temperature change of what? 68 to 90? 22?
Yeah.
Sorry, glitched. And what's that stress?
2882.
2882 PSI. And that relieves the 5,000. So we end up with 2118. Is it gone still? All right, yeah. Thermal stresses are big, like, I think aluminum is probably okay with near 10,000 PSI, but that's a lot, you know, but the temperature is changing it quite a bit. How'd 10 go? Did you get it? Steel beam, 4 meters long, placed between two rigid supports when the temperature is 16 degrees C. Compute the stress developed in the beam if the temperature rises 50 degrees. Assume the proportional limit is that.
Oh, wait.
Was it rises 50 degrees or rises to?
It rises to 50 degrees.
Okay.
Yeah,
Oh.
from 16 to 50.
That's six.
So your delta T should be 34.
Yeah.
Yeah, delta T should be 34.
Because the statement says if the temperature rises 50 degrees, not 2.
This is rises.
No, it does say 2. Yeah.
Oh, I missed the 2.
I misread it also the first time,
Okay, got
but
it.
it does rise to 50 degrees.
So I did the.
So you got a little more than you needed, right? And that's gonna develop stress, right? Because of the rigid supports. Temperature goes up or down. If you have two rigid supports, if temperature goes up or down, you're definitely developing stresses. That's why we try not to have rigid supports. That's why we've always had a pin and a roller. Right? A pin and a roller will allow that beam to expand and contract with temperature. So that's usually what we want to happen. Right? Just remember, all our beams are like pin and roller.
Okay, that's number 8, right?
10 was the one we just did. Well, we just talked about, I didn't do it.
We did number 8 first.
Yeah, we did them out of order,
8, 7.
just to keep you thinking, just to
Wait,
confuse.
so round number 10, you didn't need to care about how long it was.
No, because it's just stresses, it's not thermal elongation. Yeah. You're confused?
I mean, the order that we do and everything.
I know, it's just to keep you on your toes. All right. We don't need to work it, right? We're good?
Let's work it anyway.
Let's work it anyway. For those of us that maybe didn't work it, I think you would. For it. 4 meters long? Unnecessary, right? Between two rigid supports, what's the delta T? 24? 34. The difference between 16 and 50, 34. Yep. It's A36 steel. And the temperature's going up, correct? Yeah. So does it put this thing in compression or tension? So it's trying to expand, right? And the walls are doing what? Keeping it, so it's in compression. So that's good to think about too. Doesn't really matter, it's gonna be the same number. But, so, stress would be alpha E delta T. What's alpha for mild steel, A36 steel?
11.7 times 10 to the -6.
I did that in Asian as well.
Oh, me
And
too.
30
I did that as
million?
well.
Okay.
Let's try it again.
30 million for the modulus?
Said
207
207,000
times 10
megapascals.
to the
Are we degrees C? Oh, 4 meters, yeah. Whoops. All right, what is it?
207,000.
Megapascals.
Yeah.
Yeah. And then 34 degrees. C. What'd you get?
82.3446.
Yeah.
And what does steel think of that? Anyone got the steel memorized yet for the metric? Mild steel should be 250, right? Yep. 250 MPa just for the yield. So what's our factor of safety? So if the yield is 250 megapascals. Huh? Yeah, so you take the 250 divided by 82. And kind of round it, normally what you do. 3.048 factor of safety would be 3. It did not ask for that, I'm just tossing it out there. Pretty good design.
Is it
Yeah, it's factor
allowable
of safety.
over failure?
Failure over allowable.
Oh,
Yeah, so this would be the failure, can't exceed this number.
right. Okay.
If you don't know, this one didn't give us a number, right? Like a proportional limit or something, no. Yeah, if you're not given anything, we use the yield as the failure, unless we're told something different, so. Yeah,
What's it called? In the real world, like, is there a specific factor of safety that like people want?
absolutely, yeah. So the FAA, flying world, has factors of safety anywhere from 8 and above. Yeah, so that's why, like, when you're in that plane and you hit that storm and you get a really rough ride, it's good. So, the auto industry factor of safety varies anywhere from like 3 to 10. So those are very, life-threatening industries. The camera industry probably doesn't even think about factor of safety, right? They probably don't, but if they did, maybe it would be a 2 kind of thing.
The last 20 years, the automotive industry have increased the factor of safety.
They've increased safety big time, but I think the factor of safety on
Or it's still-
most structural pieces are about the same. Just better designs, way better designs. Yeah. It's impressive what you can survive now. Go by some of these accidents, and I'm like, oh my God, that's a fatality. for sure. You're like, nope, everybody's like broken leg or something, that's about it. All right, tournament. Tournament.
Can I have me do this?
You're not disappointed, no.
I am.
Impressed.
I did everything you needed.
Just so impressed.
Convert that.
We are overpopulated.
Did he convert it?
No, I didn't.
Okay,
I was just looking at the-
so you started to sound like me during, what's it called, the auto cap.
This is the new.
Eugenics.
Yeah, dude,
You
we
can have
are
stapler.
overpopulated.
No,
Oh, you have a stapler.
Yeah.
is it out?
What, can I?
Well, let's reload it, Tina.
I didn't know.
We're engineers.
Oh, yeah. Oh, yeah, you were in there. Oh, my God. Yeah. How would Sean do it?
What if I draw this in like base?
I'm in-
Calculus.
I'm in Sean's calculus class. We feel like right next to each other.
He was complaining about how long the. Definition. So,
Oh, it takes so long.
I'm for Sean. Sean was a silly one that would offer you, what's it called? Caffeine pills.
No pills.
Hey, no.
No pills, bad.
Bad pills. All right, the next stress concentration or the next stress consideration is stress concentrations. So these are pretty straightforward also. I mean, thermal's pretty straightforward. Two little equations, just have to figure out which one to use, right? One for stress, one for elongation.
Or combo.
Yeah, or combo.
A equals R over D.
Yeah, so for stress concentrations, there's only three situations that the book covers. There's obviously more than three in the world of stress concentrations, but this is good enough, gives you the feel for it. Beyond that, you'll be able to look up more types of changes that can happen. The changes that the book goes through is a hole. So when you put a hole in something, that is a stress riser. It's a stress concentration, right? So if I have something and it doesn't have any holes in it, then I can calculate P over A to get the average stress across the thing. But if it's got a hole in it, that changes everything. So here's the calculation P over A, and that's the stress graph. It's kind of how they do it, the stress load, right? Back in here, but then as we find a hole, the stress on the outer fibers is much smaller than the stress right near the hole, it goes up dramatically. That's called a stress concentration. So we need to be able to calculate these stress concentrations. A hole, notches, and a reduction in area. Reduction in area. So a larger area down to a smaller area. All of those are stress concentrations. Those are the only three that the book does. So beyond that, you get some other kind of stress concentration, you'll have to figure it out, right? Most books are only going to cover 3 or 4. And these are the most common ones. Obviously, a hole is super common. Try and find any structural member out there that doesn't have a hole in it. Like we put holes in everything. So notches, I don't know when I've seen notches, but that must be common.
Unless you do it on assembly. you put
Yeah.
face.
Yeah, and then I do see reduction in area quite a bit, so. All right, so how do we do it? We use a graph and figure out a concentration factor. So the equation looks very much like the stress equation. P over A, right? So this is gonna be the load. This is gonna be the area net, or the area that's left over after the change. So for the hole, the area net is the area here, right? The hole takes away some area, so we have to calculate this area instead of the entire area, right? So it's like this removed area from the existing surface cross section. And same with the notch, same with the reduction in here. So area net, area net, area net. So we have to calculate this reduction in area, and then we have to calculate the K factor. The K factor is going to be a multiplier to the stress, is going to rise it, right? And we use this graph for it. So well, let's figure out how to use the graph. So on the left are the K factors. So here's K. Gesundheit. Down at the bottom is the R to D ratio, and R is given for each situation and small d is given for each situation. It's pretty simple though. R is gonna be the radius of that hole. R is gonna be the radius of that notch, and R is gonna be this reduction in cross section. So they tell you what each R is. D is gonna be the leftover distance. So D is like from here to here, add that together, and that's small d. Here, D, straightforward, and here, D, straightforward. So you calculate this R to D number, find it on your graph, travel up to the kind of reduction you have, either a hole, semicircular grooves, or these fillets, right? And then follow it up to a K factor, or follow it over, sorry, to a K factor. So if we ended up with 0.4 and we were doing a hole, we'd come up, find the graph, and then come across and say, oh, it's a little less than 2.2. Okay. So let's do one of these. I'll just make it up. Take my structural piece of wood. And the electrician comes by. What do electricians do? Actually, let's pick on a plumber, because what do the plumbers do? Those turkeys, they have giant hole saws. So we're gonna say this thing is under, it's in a truss and it's under a load of 500 pounds. It's a 2x6. Which is really what? 1.5 inches by 5.5. Yep. And the plumber comes along and burrows a 3-inch hole. Three-inch diameter hole in our 5.5-inch board. Not uncommon, pretty common. 3 inches is kind of big, but they do 3 inches sometimes for surface lines. So what is just normal stress that we calculate? That's P over A. And then stress here at the concentration is going to be K, P over A net. Right? So back away from the hole, we have P over A. Right at the hole, we have K, P over A. What's P? 500 pounds, that's the load. What would our area net be? That's this area right here, right? That's this area right here. I'm going to shade it in. It's the area left over after you burrow the hole, right? So it's 1.5 inches this direction. And then how much is left over in this direction? Well, 3, and just take it away from 5.5. These two will combine to how much? 2.5. Yeah. So the area net is going to be 1.5 times 2.5. It's the area left over after you cut this hole out. Everyone see that? Times 3.75 inches squared. Okay, so what's my R to D ratio? What's R? Radius of the hole, 1.5. And then what's D? D is this distance plus this distance. So that's the 2.5, right?
So on that one, you do not, the 2.5, you do not delete, divide it by 2?
No, because it's this distant, it's this one plus this one.
Okay, so
It's that
both.
leftover
It's
deal.
both, okay.
Yep, yep. Good question. All right, so now we have our R to D ratio, which is what, 0.6? We can go to our graph and find 0.6. 0.6 is here. And what kind of a reduction do we have? We have a hole, so it's right up here. It's above the 2.0 and below the 2.2. It's actually below, I think, 2.1, but just barely. So this is a graph. We're gonna get different numbers, but I'm gonna say 2.08, not 09. Right there, green across, it's not quite, 2.1 would be halfway up this between the two. I think it's under that. So K factor equals 2.08, I'm gonna go with. And again, we're gonna get some different numbers when we read the graph. Everyone see how I got it? Yeah, no? You have to play with that graph. All right, so now we're ready to do our stress concentration. It is 2.08 P 500 pounds over area net 3.75 inches squared. $277. Anyone else get that? No? Yep. Getting there. Someone else get that number?
Yeah.
Yeah. Okay, good. And then what does Wood think about a tensile stress? Because it's pulling on it, right? A tensile stress of that amount. We'll say it's Doug. Design values for timber, tension, parallel to the grain. Here's the grain. Because we do make our lumber out of trees, and we make our lumber out of the long part of the tree, not across the tree. So it's definitely parallel to the grain. What do we get? Doug fir, tension, parallel to the grain, 625. 625, 277, we're good. What's the stress out here? Just the normal stress, average stress on this piece away from the hole. That's just 500. And then the area is that right there, 1.5 by 5.5. 60.6. So the stress here is 60.6 PSI. The stress at the stress concentration, 277. 4 times bigger where we pop that hole. There is code to plumbers and they can only do that one time in a structural member, so. Yeah. They have some ratio they have to go by. Like you can't remove more than 0.6 of the material, something like that. That's stress concentrations. Another stress consideration. So yeah. You have some homeworks in that, I believe. I think I said. Oh. Oh, wrong class. You're gonna do 17 and 18. There is a quiz tomorrow, comes available at 12:01 a.m. And then goes to bed at 12:59 p.m. So don't miss the quiz. There is an upload location for it this time. I can verify that. So
Sure.
that's not gonna be an excuse, Jorge. You can't send it to me via email and say I can't upload it.
I always send it by.
I know you do, every time.
I can't load it on the Blackboard.
All right. Good job, y'all. I made this on our printer yesterday.
Oh, camera's on.
So we're practicing. Nobody in here in the additive class, right? Oh, Jorge is. We're practicing the tolerances and trying to figure them out on the printer. And we're also practicing printing assemblies.
So you end up printing it?
Yeah, I printed mine. And the little one, I threw it away. The little one didn't work. It was all welded up, so I double scaled it. And it worked great. I mean, it put some support in there. But I had to bust it free, but now it's like, it's perfect. So fun.
Try this. What do you mean?